All right, thanks a lot for the introduction and thanks for inviting me. That was great. I don't need to motivate anything. So everyone is motivated for thinking about robots and autonomous systems that interact with people. So I'm Dorsa. I'm in computer science and electrical engineering, and my research is about algorithm design for robots. So I'm very interested in designing algorithms for robots that can actually interact with people and are safe. So when we think about these autonomous systems or robots, kind of the immediate pictures that might come to our mind are things like this. So we might have things like autonomous or semi-autonomous driving, or controlling drones from the ground. We might have things like service robotics, so like doing tasks with robots in our homes, let's say, or like robotic surgery. And I know these systems are very different from each other, but one common thing that they have, one thing that they have in common with each other is that they're all safety critical and they all need to interact with people. So each one of these systems is quite challenging. There's a lot of engineering behind getting these things working. But the common aspect here is we want to care about interaction and we want to care about the safety of some of these systems. And when we think about our robots today or autonomous systems today, they're not very safe or they're not very interactive. And I have some videos here that I was going to show. So, so this is from the DARPA Robotics Challenge in 2015. I'm sure a lot of you guys have seen this. Any roboticist that gives a talk, this is kind of their first slide, that look at all these robots, that is kind of the state-of-the-art robotics, but they fail. Which is true, they do fail, but there are some success stories there too. And there, as I said, there's a lot of engineering, there's a lot of hard work that goes into designing these systems. So yeah, so this is 3 years ago. And as you can see, our best robots today are not very good with dealing uncertain situations or dynamic situations. And it's not just robots, it's autonomous systems in general. So here I have this video from the Tesla autopilot crash where the vehicle doesn't detect the car on the side of the road and there's this fatal crash. And also when it comes to interaction, we're not that great, especially if that interaction is with people. This is one of my favorite videos. So in this case, the person has no idea what the quadrotor is going to do next. And then because of that, he's really scared and he doesn't know how to interact with the quadrotor. And if you're thinking about designing algorithms for these systems, we should really think about interaction and we should really think about the safety and some of the issues that goes on when we are thinking about design of algorithms for robots. So, so in my research, every time I think about a robot or an autonomous system, there's usually a human involved and there is an interaction between them. And the core problems that I'm very interested in is at the intersection of a bunch of different fields. So I'm interested in safe and interactive autonomy, and that requires a bunch of different fields. It's not like a single field that can come and solve it. So we are interested in learning and control and optimization because at the end of the day, I want to control this system. I want to control my robot arm. I want to control my autonomous car. And there's a lot of learning and optimization going on there, which becomes very important. I also want to interact with people, and there's this emerging field in robotics called human-robot interaction. And the idea is, let's think about how humans act around us and how we can predict what humans are going to do next, and based on that, plan better. So it's not as much about cognitive science or getting into people's head. It's more about better design of algorithms for robots knowing and predicting what people are going to do next. And the top area I've put there is this area called formal methods, which is an area in computer science. It's actually not taught in many schools. So when I go to some schools, they don't even know what it is. But it's basically this area which is about proving guarantees and providing correctness about systems. So these systems could be programs, could be circuits, could also be controllers for autonomous systems, could be a policy that's running on my robot. So what would be interesting is to look at the intersection of some of these fields where we can bring in formal methods ideas and talk about correctness of some of these systems. At the same time, we can bring in human-robot interaction and think about the interaction between humans and robots and do algorithm design. So that's kind of the area I'm very interested in. Today, I'm mainly going to talk about human-robot interaction and how that comes in. I'm not talking about as much about formal methods. There are implications of safety, but I'm not talking about that as much today. So, all right. Okay, so I know I've motivated the problem to be about any general human-robot system. And almost everything I say today applies to almost any human-robot system. But I want to focus on autonomous and semi-autonomous driving as the main subject of this talk. And when we think about autonomous or semi-autonomous driving, maybe the first thing that would come to our mind is Google's self-driving project. So that was one of the they were one of the pioneers of thinking about autonomous or semi-autonomous driving. And they started with this notion of having semi-autonomous cars where the car was driving autonomously on highways because that was easier. And whenever it was getting off a highway, it would basically transition control back to the person, telling the person, I'm getting off the highway, this is too difficult, you got to come and take over control. And city driving was human-driven. But all of a sudden, in May of 2014, Google decided to completely change their plan and come up with this new design which has this fully autonomous vehicle and go with this fully autonomous vehicle and eliminates the steering wheel and braking pedal and completely eliminates the human driver. So they decided to have this new design of fully autonomous cars. And actually, I remember at the time I was at Berkeley, and Anthony Lewandowski was working on a project, came and gave a talk at Berkeley. And he actually mentioned one of the reasons that they're going fully autonomous is modeling humans seems very difficult. And this is the human inside of the car. So thinking about what the human inside of the car is going to do next can be very challenging. And they decided to just get rid of the humans, have this new design. But then if you look at where Google went immediately after that, well, they have these monthly reports. And in only a span of a few months, they had 11 accidents. In all of these accidents, the Google car was being rear-ended. So of course, it wasn't Google's problem. It was the other car's problem. But the question that came to my mind at the time was, well, why am I not being rear-ended 11 times in the span of a few months? Yes?
Well, how much were they driving?
Yeah, and then, so I would say, well, maybe Google is driving way more than me. Google is driving so much. And the actual numbers is actually in the report. I don't remember the actual number. But of course, Google is going to drive more than I drive. But why am I not being rear-ended that many times in years of driving? In years of driving, I only had one accident in my driving experience of years now. And if you think about it, this is not a problem just with Google. This is a problem with most car companies. They're trying to put these vehicles in a world where humans don't behave by the book. You might assume humans are going to follow all the rules and drive at 15 miles per hour. But humans are not going to really do that because they have their own kind of rules of playing when they're on road. So we started looking at a picture that kind of looked like this. And this kind of motivated our research. So even if I eliminate the driver inside of the car, there are still human-driven cars around me. There are still pedestrians around me. And I actually need to think about the interactions between these other agents.
I might make a comment because this just happened on my way here today. And that is, it's no longer just cars. I passed a Waymo 18-wheeler. And so they're driving big trucks now. And that was on 280. So it's not just cars anymore. You should get a photo of the Waymo.
Of the Waymo truck.
Yeah.
Yeah, trucking is, a lot of people think trucking would be the first thing that would be automated because highway driving is easier, right? So if you can have trucks automated on highways, that can solve a lot of problems. But yeah, so we started thinking about this problem and started thinking about autonomous cars. And if you think about autonomous cars, well, autonomous cars today, they try to optimize for reaching for their destination. So they try to go towards their destination. And at the same time, they try to avoid unsafe regions of the road, like the boundaries of the road. And if there happens to be another vehicle on the road, they usually treat that vehicle as a moving obstacle. So basically try to do collision avoidance with this moving obstacle. But if you think about it, this vehicle is not just a moving obstacle that happens to sit there, right? There's a human inside it, and the human has a model of the world and also plans for reaching for his actions, so his goals. So think about it, whether we want it or not, or whether we plan for it or not, the actions of an autonomous car actually affects the actions of other drivers. And we actually need to take that into account. We need to think about these effects and responses. And we do see these type of behaviors in our everyday lives. For example, if I want to change lanes, I don't assume this car is a moving obstacle. What I do is I start nudging in front of the person and I expect the other driver to slow down and respond to my actions and then make room for me. And that's how I change lanes. And unfortunately, that's not currently how autonomous car companies do this. This is actually a recent video of a Waymo car, where the car is trying to change lanes because it's in the exit lane. And it starts signaling, doing everything right, but it just can't do it because it doesn't think about the actual interaction that goes on between its actions and the other agents. So it has to actually exit, come back around, and do it again. So this is a problem, right? Our cars, our autonomous cars today don't really drive human-like in some sense. Or thing.
Driver's test. This is that.
The driver's test?
I've passed my driver's test. Aced it. And there's a section in there on that subject.
That does that?
That rules how to get in and out.
How to get in, yeah, in front of people. Yeah.
What happened? No computer ever read a driver's test?
Driver's test would be interesting to have, yeah. No.
Should that be the goal? At least to me, that sort of sounded obvious when I did it.
But like then you have to kind of, what if you miss a goal? So every time like you write like you have to come up with a rule book of like all sorts of things to try, and you would always like miss something. So you want to have something that is a little bit more like less hand codey, like I would put it. It would be awesome. Like I'm not suggesting we have that today. It would be awesome to have something like that. So we started thinking about this problem, and we thought about modeling this interaction that goes on between an autonomous car and a human-driven car as a dynamical system. So what I mean by that is I have direct control over the actions of the autonomous car. So that's, let me call that UR. So that's the steering angle and acceleration for the autonomous car. And in some sense, we have indirect control over the actions of the human-driven car. Let's call that UH. So also that's the steering angle and acceleration of the human-driven car. And when I say indirect control, what I mean by that is, well, if I take actions, that should affect the actions of the humans. So in some sense, I can indirectly make humans do things. And this is kind of like an under-actuated system. If you've taken a controls class in electrical engineering, you've probably seen under-actuated systems. And this is kind of like an under-actuated system. So more specifically, what we are doing here is we're trying to find these actions for the autonomous car that maximizes some objective, some reward function. And that reward function is a function of state and actions, which is usual. But now I'm saying this reward function should depend on the actions of the human, should actually affect humans. And the good question to ask is, well, what does the human do? I'm putting UH star there as kind of these optimal actions that the human is going to do, this model of the human. And a good question to ask is, well, how do I know what UH star is? Where does UH star comes from? So the way we are modeling the human in this work is we are assuming that our humans are approximately optimizing their own reward function. Let me call that RH. So they're kind of, this is like, if you want to remember one math from this talk, this is kind of the math that to remember. This slide has a lot of questions in it. So the first question is, well, okay, now that I've put RH here, well, how do I know what RH is? Where does RH come from? What does it mean to have a reward function of the human? How do I come up with UH star now that I know it's RH? Like, is it fair to assume that humans are optimizing a reward function? What if they're not optimizing that? What if like we are in a near accident scenario and the human is not really doing that? So now that I have that, let's say I have the perfect knowledge of predicting what humans are doing. Even if I have that, I'm putting it up there. How do I go about solving that top optimization? So this is a nested optimization. Each one of these reward functions are non-convex, non-linear functions I need to optimize in real time on the vehicle to go. So like even optimizing that, even if I know everything, can be quite challenging. And then another question is, what should be the reward function of the robot? So what is RR? Like that's a reward design problem. Like what is a good reward function to put on the autonomous car? So I want to just briefly talk about some of these questions. I want to first talk about the reward function of the human, unless there are any questions on this slide.
So if you have many different vehicles, do you like do different weighting for each of them depending on the action desired of the robot?
Mm-hmm. So if we have other vehicles that are kind of in our local vicinity, we do take into account their actions into the formulation, and yeah, we assume that we can affect them. But most of our work, we just consider the closest vehicle to me and think about the effects and responses just between the two cars. We are doing some work now that's thinking about it from the transportation perspective, of if I throw in like a few autonomous cars, how can they help with something like traffic? But we're taking a very different view there. So like it's a very higher level network level view.
I taught control theory. To me, that's a MIMO problem. Multi-input, multi-output. Right? You have this asymmetry.
So, so the
Yes,
reason
one is a human, one the other is a computer, but still.
So you can think of this as a game theoretic way where you don't have asymmetry, like you actually have symmetric, my actions can affect you, your actions can affect me. Computationally, you can't really solve that in real time.
You have fast algorithms for that.
So, no, if I have, well, these are nonlinear, non-convex functions.
I know, they're fast algorithms for nonlinear. But anyway.
But they're not going to, like, they're going to fall into, like, local optima anyways. They're not going to, like, solve.
If you do just, well, I talked to you
yeah, let's chat about
Deep learning does not solve that problem.
I'm not running deep learning.
I know, I understand. Making a bad joke.
All right. Okay, so let me talk about the reward function of the human. So what is that? Like, what are we actually doing in figuring out what the reward function is? So the way we are approaching the problem is running this algorithm called imitation learning, or specifically inverse reinforcement learning or inverse optimal control, same thing, which is this idea of let me collect trajectories of how humans drive, and then from that learn a reward function that if I optimize that, I would get the same trajectories. So it's learning from demonstrations. I collect demonstrations of how humans, like let's say, pick up an object, and from a lot of these demonstrations, maybe I can figure out a reward function that if I optimize, I can get the same sort of behavior. And the specific assumption we are making here in this approach, which is called maximum entropy inverse reinforcement learning, is probability of actions of humans is proportional to exponential of a reward function. So all that means is if I have an action that I think is better and it's going to take me to a better state, I'm going to weight that action exponentially higher. So that's kind of the only assumption I'm making on how humans are driving. And you also need to kind of like put a structure around this reward function. The specific structure we are putting here is assuming that it's a linear combination of a set of hand-coded features. So these are things like collision avoidance or staying within your own lane or road, or like these sort of heading or your velocity, or these different type of features that are representative here. So the thing that I would want to learn at the end of the day are the weights of the features, assuming that it's a linear combination of these nonlinear features. And with this approach, I would have a model of how normal human drivers are going to drive. So I would have this reward function that I can learn offline from gathering trajectories of how humans drive. And then I can put that back in here, and I can go about solving this nested optimization. So we have to make a few approximations here to make this actually work in real time. So I want to go through like some of these approximations. So the first approximation is, well, first off, we don't have full knowledge of the world. So what we are going to do is we're going to apply this approach called model predictive control. And the idea is I have a horizon, and I'm going to pick that horizon, plan for that horizon, take a step, and then replan. And the horizon I pick is based on how much my sensors can sense, or based on how much computation power I have. I might have like so much computation power to actually optimize this in real time on the vehicle. And so this is the common approach that we do. The second assumption is going back to this game playing thing that I was talking about. So if you think about it, the actions of the robot affects the actions of the human. The actions of the human affects the actions of robot. Robot might know that and even like go further in. Human might know that and then go further in. And we might have like infinite regress already here, like me affecting you, you affecting me, and that'll go forever. But the way we're solving this is actually as a Stackelberg game or as a leader-follower game. And the idea is you're cutting the game at the second time step. I'm assuming my robot is thinking it can affect the humans, but the humans are observing the optimal actions of the robot. And the reason that this makes sense or works in this setting is humans don't really play chess when it comes to driving cars. Like, they're not thinking that many layers down. There's actually psychology studies that talk about the fact that humans only think 2 levels down when they're driving. Like, they're not thinking about the effects of their actions so many layers down when they're driving. So in that sense, this is sort of okay. And another reason that this assumption doesn't hurt us too much is we are solving this in a model predictive control fashion, so we are replanning at every time step. So even if I make an incorrect kind of decision, even if I don't like do the right thing to do here, I can replan and kind of come out of it in the next time step. And our planning horizon is like 0.1 second. So we're planning for every 0.5 second, but the step is 0.1. Yeah? Any?
Only half a second ahead, the horizon.
So the MPC horizon, sorry, is 0.5, but the time step is 0.1. Yeah, so if I plan for the next 0.5 seconds, I take a step, next 0.1 second, I'm in a new place, and I keep going. Yeah.
How does that interact with the human reaction time?
That's a very good point, yeah. Yeah, so there are studies looking at how human reaction, there are studies that talk about human reaction time, and they can range from like 2 seconds to like 8 seconds, right? Depending on how much they're in control and not, and whatnot. So yeah, so in this case, this is the kind of reaction time of the autonomous car, right? So, and then you're just observing where the human is, and you're not really like putting in human reaction time in this setup. There's another work that I'm not talking about it in this talk, where you're doing transition of control to the human, and there we're actually thinking about human reaction time and how much can I plan further, and like bringing in this idea of human reaction time into the story. But yeah, human reaction times are not that great.
How much memory of the human, the observed human behavior do you have? Example, I will be driving along and I'll notice somebody twitching, but they'll sort of go normal. But I'm going to keep watching them because those are the cars that tend to just take it across 3 lanes.
Yeah.
Or if you see, and you're in Anaheim, by a particular exit, you see a car 2 lanes over to the left, you know it's going to cut across you to get on Ball Avenue.
Yeah. I'll come back to that. Okay. So I'll come back to that in a few slides. And then I'll come back to your question, because like the 2 slides from now, it sort of answers the question, but doesn't completely. Let's come back to that. All right. So and then finally, the final assumption we are making here is when you're modeling humans, you're modeling them as probabilistic agents who are approximately optimizing this reward function. But when it comes to planning, which is when we are solving this nested optimization, we are actually like assuming our humans are deterministic and are deterministically picking the maximum of the reward function, as opposed to approximately optimizing it. Again, the reason is timing. So the reason is I could technically say the human is approximately optimizing this and kind of add like a noise factor into it, but that can mess up the timing of my optimization. Okay. All right. So then when we try to solve this problem, the type of, like, as I mentioned, these are nonlinear, non-convex functions. So the best really that we can do these days is to use gradient descent type approaches. So specifically, we are using quasi-Newton techniques for their fast convergence. And even doing that is not that easy. So if we're doing something like gradient descent in this setup, I need to have a model of I need to have an expression representing my reward function, the thing I'm optimizing, reward function of robot. So I already have that. I also need to have an expression for the gradient of the reward function with respect to a decision variable, which is UR. And following chain rule, I get that expression. And this particular expression is actually not that easy to find all its elements. Specifically, this term is the term that I can't just immediately have the value for it, which is exactly how much the actions of the robot is affecting the actions of the human. So this is that gradient is specifically specifying that amount of value. So what we are doing in this case is a math trick, really. So what we are doing is we're using implicit differentiation. We are taking the reward function of the human. That's a function. I can take its derivative at the optimum, which is UHS star. So I can take its gradient with respect to UH at the optimum. That should be equal to 0. That's only true if my function is nice, which is nice in my case. Then I can take another gradient of everything with respect to UR, and that's also equal to 0. And pretty much every term here can be computed except for this term. So I can solve for that term. And that's exactly the missing term that I had up there. So I can basically use this math trick of implicit differentiation to extract out this gradient, put that back up there. Now I have an expression for my gradient. I have an expression for my function. I can use my favorite quasi-Newton method to go about solving this. So specifically, we're using this method called LBFGS and using TensorFlow to optimize things. Okay. All right. So let's look at some of the implications of this. So imagine I have an autonomous car, that's the orange car. I have a human-driven car, that's the white car. And let's say the autonomous car wants to change lanes. It wants to go to the left lane. So normally what autonomous cars do today is something like the Waymo car. So what they do is they look at the velocity of the human-driven car, they project that, and they want to be safe, so they do something like this. They slow down and merge behind this vehicle, so go behind this vehicle. What our car does, based on this nested optimization thing that we are running, is actually something different. Our car decides to act a little bit more aggressively, and it cuts in front of people.
That's not according to the handbook.
That's not according.
The handbook says you have to slow down behind it.
But then that way you never can change lanes. Like, have you driven on 101? On 101, if you want to change lanes, and if you don't cut in front of people, no one.
Your robot will not pass the driver's test.
Wrong.
It's your talk.
Yeah, so well, I would say this is more human-like. I agree that this is not, like, this might be a little bit more aggressive even, right? Like, cutting in front of people doesn't seem that safe. If I want to have autonomous cars that are super safe, this is not a very safe thing to do. Like, doing that, by doing that, I'm actually, like, not violating safety conditions, but putting myself at more risk of colliding even. But I'm actually arguing that not doing that can also put you at risk, because if you're driving and waiting for every car to pass, like maybe the car behind you doesn't realize that you're driving you're driving more mechanically and might actually hit you from behind. So and as I said, like I think humans drive like this. A lot of times humans start like nudging in and cutting in front of people and making other people slow down by their actions. And this is if I have a true model of the human. So in this case, I can only do this if my model of the human-driven car is very good. If I know exactly this human-driven car is going to respond and slow down. Okay. We also saw some interesting other behaviors that are definitely not human-like. So what we saw was running this algorithm, we had the scenario when the two cars arrive at an intersection at the same time. And the autonomous car, the orange car here, is rewarded for making the human go first. So it really wants the white car to cross first. This is actually the heat map of the reward function. It really wants the human car to just pass first. So what our car decided to do in this setting was a little bit surprising. Decided to back up. Like, what is this car doing? But if you think about it, by backing up, the car is making more room and making it safer and more likely for the human car to cross first. And I've never seen any car, autonomous or not autonomous, back up at intersections. I completely agree with that. But I've seen pedestrians do this. A lot of times pedestrians back up, tell you that you should cross first, I'm not crossing. So it was kind of interesting to see that the car just decided to use motion to coordinate with the other driver without like hand coding anything of, oh, I'm at an intersection or not. Like it just decided to use motion to better like coordinate with this other agent.
It's called signaling.
It's called signaling, yeah. So we don't have, so if we have an actual signal, like we might actually get signaling behavior. But in this case, the only thing we have control over is motion. Like that's the main thing we have control over. Behind it, what would happen? That always comes up. It's not going to back up. It does have collision avoidance. It cares about collision avoidance more than like doing like this type of behavior. So there's a balance between the different things that it's optimizing. Collision avoidance is definitely the first thing that it would optimize. And the interesting thing is this is something that we get in human-robot interaction too. Like if I have like a robot interacting with me in a home setting, we are actually interested in using motion to coordinate with people better or use like legible motion that's more like expressive for the human to do things. And it's kind of interesting to get more expressive motion from cars in this setup, and they decided to coordinate. So of course, none of this makes sense unless it works with real people. So what we decided to do is we decided to do a user study where we brought in users to drive on a car simulator with a steering wheel and braking pedal. So this was a very simple simulator, but we actually did some studies later with fancier simulators where you would actually feel the forces. This is like very simple. But what we saw was for this scenario when the car decides to back up, the ideal human crosses first. So being on the other side of star means crossing first. And the purple trajectory corresponds to the ideal human. And by ideal human, what I mean is this is the learned model of my human. This is from inverse reinforcement learning. This is me simulating what the human would do if the human were to follow this reward function I've learned.
Where did you get your data from?
So the driving data to learn IRL or the user study, both of them from users in like lab. Yeah, both of them were grad students or undergrads like running on the simulator. Yeah.
Known for their good driving.
What's that?
Known for their good driving.
Known for their good driving, yeah. And what we saw was, well, our users do something very similar to the ideal human. So the orange trajectories corresponds to trajectories of real users. This is the average and standard error of what the users do, and they all cross first. So they do something similar to the ideal human, and they all cross first. But if I'm not planning with a human model, if I'm doing the usual thing of just planning for the autonomous car without considering any human models, what my users decide to do is something very different. They do the gray trajectories, and they all cross second. So the gap that we have here between the orange and gray trajectories is actually the gap that we can create by just modeling humans and how they would respond into our planning algorithms, which I think is kind of cool. All right. So I think we all agree to generate safe motion, we need to anticipate what this human-driven car might do next. And one way of anticipating that is by modeling the human as an agent who is approximately optimizing maybe some reward function. That's one way of modeling the human. But then we kind of ran into this video, which was a little disturbing. So this is a video of a truck driver. Let me see if this runs. And then there is a vehicle on the side of the road. It's signaling. It's doing everything right for changing lanes until like now. And for some reason, this truck driver is not letting this car in. Yeah. So you might say maybe the truck driver was asleep or very angry or completely out of it. And the other driver was kind of aggressive too. He kept pushing. If I was the other driver, at some point I would give up. I would go back to my lane and be like, this car is not letting me in. I'm done with this. Like, this is not happening. So if you think about it, well, different drivers have different driving styles. You might have aggressive drivers or timid drivers, or you might have distracted or attentive drivers. And when it comes to modeling humans, we can't just rely on a single driving style where we assume everyone follows the same reward function and we can just go with that, right? We actually need to differentiate between different people's driving styles and different ways that people respond to our actions. So we thought about modeling that into our formulation, and that was kind of what we decided to do next. So we took our formulation, and we just added a term. Let's call that term theta. And theta here just represents driving style. And what I can do is I can have a belief over the driving style, and I can update that belief at every time step based on the observations that I get. So observations would be how this car is driving right next to me. And the observations is probability of actions of the human-driven car, given the state and theta. And I can just update my belief of how the car drives. So this kind of works okay, but there is a problem with this. And the problem is we got to get lucky to see any informative behaviors from the white car here. For example, if I have this turtle, it looks harmless, and I might go my whole life thinking that. But it's only when you start poking the turtle that you realize what sort of turtle you're dealing with. So currently, you're kind of stuck in the turtle situation. You have the orange car. It's kind of observing the white car. It doesn't really know what the white car is going to do next. But it's just doing passive estimation of the behavior of the white car. But if you think about it, the autonomous car is not just the passive observer that sits there, right? It's also an actor. It can take actions. And we have already seen like its actions can actually influence other people, right? You can cut in front of people and make other people slow down for you. So you can actually make other people respond. So, yeah.
Do you consider this analysis the fact that the cars that are being driven by people can also be automated and can have interactions with
So if every car was autonomous?
Well, not every car autonomous, but there was a way that they can communicate. So they're signaling when they
coordinate.
Yeah, so if cars were connected, or they could like
sort of,
so there's a whole there's a big literature on connected vehicles. So
not necessarily autonomous, but
connected.
What connected vehicles? Yeah, so there is there's a whole literature on autonomous vehicles. There's a whole literature on just connected vehicles. And yeah, people definitely like think about like maybe we should change the infrastructure so cars can actually communicate with each other. That sounds like a very reasonable thing to do. So there's a lot of research there. In this case, no, we haven't like looked at like communication as much, like explicit communication as much. But that could like solve many problems. And if all cars were autonomous and they could communicate with each other, like we didn't need like traffic. We wouldn't need traffic lights. Like everything could just like go through. And there's actually research that tries to like show that too.
But you can make a Markov model.
Markov model
for the other driver.
For the other driver.
So if you can find out if the guy is aggressing, goes ahead. So you feed in behind him the legal way. You're not supposed to do that. You're supposed to slow down according to the
according to that. So maybe what we are doing is so let me go back to what we are actually doing.
I understand.
And then we might be doing something that's a little safer.
Don't apologize.
Martin, just keep it moving, okay?
Yeah, I'm keeping it moving, yeah.
So what we actually do is we try to bring in these actions, these URs, into our formulation. And then what we are optimizing for the reward function of the robot is now a combination of reaching the goal, which is what it was before, this is what I was doing before, and another term that corresponds to information gain. So this is the difference between entropy over belief of driving style of this guy in this time step versus next time step. How much information can I get about this driver? So while I'm doing this, like when I'm optimizing this reward function, my autonomous car is trying to reach its goal, but at the same time, it tries to kind of gain information about, is it safe for me to cut in front of this person or is it not? So it tries to like get as much information as possible. And lambda here is the usual trade-off that we would have between exploration and exploitation. A lot of robotics type work. So there's usually this problem of like, how much should I explore? How much should I exploit? And we are using standard techniques for setting lambda there. So then my robot is going to optimize an expectation over the reward function, because this is probabilistic now. And what we see is for changing lanes, if I don't really know what type of driver the white car is, my algorithm, the thing it decides to output is it decides to kind of nudge in, like creep in a little bit to see what happens. And if it decides the white car here is a distracted human, it goes back to its lane, realizing this other driver is not going to let me in. This is not going to be a safe thing to do. But if it realizes that the white car in this case is attentive, it completes the merge because it knows that this vehicle is actually going to slow down and make room for it. So it kind of updates that reward function on the go online to do a better behavior and safer behavior in this setup by doing active information gathering. So again, we decided to do a user study. So in this case, we had distracted drivers. Distracted drivers were playing a game on a mobile phone. They were playing Candy Crush because I was obsessed with Candy Crush for a period of time. And what we saw was for an intersection scenario, this is a different intersection scenario. This is two cars arrive at an intersection, but the orange car wants to cross. It doesn't necessarily want the white car to cross first, but it doesn't know what type of driver the white car is. So if you're doing passive estimation, with passive estimation, the autonomous car decides to just sit there, just like does nothing. It sits there. And with passive estimation, it becomes really hard to differentiate between distracted and attentive humans. They almost do the same thing. So these are like data from real users. Again, like I have the average and standard error of different users that I have in this case. But if I'm doing active information gathering, my car decides to nudge and creep in a little bit. And we actually see the behavior of the autonomous car here. It decides to nudge in. And if it decides the person is attentive, it keeps going forward. But if it decides the human is distracted, it slows down and even goes back at some point. And when the robot does this, when the autonomous car does this, what we get is we actually get this type of behavior, and we can easily differentiate between distracted and attentive humans because they respond very differently. So the gap here is kind of the gap that our algorithm allows us to create, because attentive drivers kind of slow down and let you go first and don't cross. On the other hand, like distracted drivers don't see you and they continue like going. And we can even have like a look at the belief of driving style, which was kind of the term we were looking at. So if in the case that people are attentive, belief of attentiveness with active information gathering goes higher, but with passive estimation, it almost stays the same throughout. So it becomes really hard to kind of figure out what people are doing. So kind of just to summarize this part of the talk, really the key idea here is that robots' actions affect the actions of other drivers or other humans around them. And the thing we wanted to do was we wanted to actually model those effects and responses, and even more than that, leverage those for better safety, efficiency, coordination, and even estimation, like as we see in the active information gathering world. Right? How much time do I have? 15 minutes?
45.
Oh, really?
No, 13 technically.
Was it
but
4:30 to 5:30?
Technically, there's no class till 8 in the morning, so keep going.
I can keep going. Just checking. So don't worry, the second part is not too long. But I was wondering if I should skip parts of it. Yeah, so that was kind of the big idea that we had kind of in this setup. And then we started thinking about the human models a little bit more carefully and thinking about, well, what is it about the humans that we really care about, like looking at and thinking about. And yeah, as you've seen already, well, different people might have different preferences about how any given robot should act, right? And the problem is getting demonstrations. So the way we are doing this right now, the way that we have modeled humans is by using inverse optimal control or inverse reinforcement learning, where we collect trajectories of how humans do things. Like we get demonstrations from humans. But getting demonstrations from humans is always not that easy. Actually, demonstrating trajectories for robots with more than a few degrees of freedom can be quite challenging. So there's actually work trying to look at teaching robots to do tasks. And when you have a robot with like 7 degrees of freedom, it becomes really difficult to demonstrate a good trajectory and even teleoperate that robot to do a task in a way that is preferred. So first off, demonstrations can be really challenging. So is that even a good way of thinking about humans? The second issue is there's a study that looks at driving demonstrations. And what they saw was they collected driving demonstrations and replayed the same demonstrations to the same people. And apparently people don't really like how they drive themselves. It turns out they think their driving is aggressive and they prefer something that's a little bit more conservative than their own driving. So then if that is true, then driving demonstrations are not even that informative of humans' preferences of how a car should drive. So we started kind of thinking about this other idea that maybe instead of demonstrations, we can leverage comparisons as opposed to demonstrations, which can be very useful observations of how a robot should act. And what I mean by that is, what I can do is I can have this fetch robot that's going to do 2 different trajectories, and I can ask a user, well, which one do you prefer? You don't need to teleoperate this. You don't need to like actually get the robot do any of this. But which one do you prefer? Like what if you were to compare these two, which one do you prefer? And the human's response gives me information if the human really wants the blue cup or the red cup in this case. In driving, we can do a similar thing. We can show 2 different trajectories. Let's call those psi A and psi B. And we would ask humans, well, which one do you prefer? And in this case, the human's response gives us information about that reward function I've been talking about. So I was trying to learn a reward function representing what the humans are doing. And if the human tells me, well, I like psi B over psi A, that gives me information about which reward function is preferred. So that gives me information of w.phi B is greater than w.phi A. And W are the weights, the things we really want to learn. And phis are these features, these hand-coded features about each one of these scenarios, and they're evaluated at scenario A or scenario B. Okay? So let me just move things around a little bit. So the question I'm really asking is, let me define this new phi. And the question I'm really asking every time from the human is, tell me if W.phi is positive or negative. Like I'm just asking which side of like the hyperplane of W.phi I should be looking at. So more specifically, so imagine W lies in a 3-dimensional space. Let's say that I only have 3 weights. So if that is the case, well, I can actually assume that W lies in a unit ball because the sign of W is the only thing we care about. We don't actually care about the value of W. The sign is the only thing we are trying to learn. And we can sample from this space. And every time I ask the human a question, that query or that question corresponds to a hyperplane in this space. So that's the hyperplane of W.phi equal to 0. And the human's response gives me information about which side is preferred. So if the human tells me w dot phi is positive, I would take or negative, I would take either side of this hyperplane. And then, well, what I can do is I can reweigh things. So I'm going to reweigh my samples. And I'm not completely removing the other side because we are assuming humans are noisy, so they're not going to answer every question accurately 100% right. This is actually the noise model we are using for the humans, which is using the Boltzmann distribution for how humans act, backed by some psychology literature. So this is my first question. Every time, like, this is my first question, the human tells me that it's on this side of the hyperplane. So the second time that I'm coming up with a question, with a query, it really matters, like, what hyperplane that query corresponds to, right? I might pick a question that corresponds to a hyperplane that gives me the exact information and quickly converges to the thing I care about, or I might ask another question that doesn't give me that information at all, like it would be a hyperplane that's not that informative. So we're kind of modeling this problem as a volume removal problem. Like if there's a volume here, I'm trying to remove as much volume as possible to quickly converge to the particular W I care about, and do this in an active manner with the minimal number of queries I would need from the human. So the idea is, when we are thinking about generating these queries need to be generated actively. We should look at like the response of the human from the previous time step and use that response to actively generate the next query. And the big challenge here is that when we are thinking about these queries, these questions that I'm asking the human, like these queries can lie in a very high dimensional space. It's a continuous high dimensional space, and I need to think about the initial position of all the vehicles and the environment. I need to come up with the trajectories of all the other vehicles in the world, and I also need to come up with two informative alternatives for my own car. And then this can be quite challenging because we are thinking about this continuous high dimensional space. And usually how people approach this is they discretize the world and they try to sample from that discrete world. But the way we are doing this is, instead of discretizing the world, we are directly synthesizing these queries from the continuous space. So we are solving this as an optimization problem, as opposed to like discretizing the world and sampling from that. So more specifically, this is the optimization. So the problem we are solving is we are trying to find a set of queries, those are phis, that maximize this minimum volume removed at every time step. So this is a volume inside of that unit ball that I was showing you. And then this term here is just representing the minimum volume removed using that specific update function that we have up there, subject to the fact that these queries correspond to reasonable trajectories that are actually realistic and don't collide with each other and are reasonable. So this is kind of the problem that allows us to create these queries. And this is a submodular optimization because our objective is volume removed here. And we actually have methods that can do this quite fast and minimize the number of queries like required to learn a model of the human. Yeah. So let's look at some of the convergence results. So what we saw was our method converges much faster than non-active methods that don't consider this previous response of the human. And in addition to that, it even converges faster than methods that are active but discretize the world. So when we're continuously generating these queries, we can actually converge much faster. And what we saw was, well, we actually ran this user study where we asked users and asked for their preferences in a driving scenario. And what we saw was, after like around 40 queries, different users converged to very similar and reasonable weights for each one of these features. So we had 5 features for the driving case. These are the different features for the driving case. This is the before figure of what the weights are. And as you can see, the weights are converging to very similar results. So each line corresponds to a user. So all users kind of prefer very similar type of driving style. There are some differences between like the purple one. Let's say purple one is for collision avoidance. So we kind of see different convergences between these different users. And in addition to that, well, what we asked our users was if they prefer this reward function that's learned as opposed to other reward functions, like perturbations of the reward function. It's small and large noise. And what we saw was the learned reward function from preferences is actually quite, like afterwards, people were very happy with this particular learned reward function, and it kind of represents what humans want in driving. Okay. All right. No questions so far. So this is kind of cool, right? This was the formulation. We're doing active learning over humans' preferences. We're coming up with a minimal number of queries to quickly converge to humans' preferences. And kind of our objective was, I want to do this fast. I want to come up with the minimal number of things that can do this fast. But the problem with this optimization is, well, synthesizing the queries themselves is a little too slow. So sure, I have like only 10 queries, and with 10 questions, I can figure out what humans want. But I ask my first question, and then I wait like 20 minutes to come up with the next question, and then I wait another like 30 minutes to come up with the third question. So synthesizing each one of these queries can be really slow. And the other problem is humans' responses come in sequentially. So if you're doing this active method, you actually need to wait for the response of the human to synthesize the next one. So we have kind of this sequential process, and you have to wait for too long to actually get the answer for your optimization. So the idea that we had was, well, maybe instead of synthesizing these new queries at every time step, let's just synthesize a batch of queries. Let's just pick a good batch of queries. If I have that batch, I can even parallelize things. If I want to learn the preferences of a population, I can parallelize that, and that's probably good enough. And that can make things much faster if at every time step I'm computing a batch. So that changes the optimization to something like this. So every time I'm running this optimization, I'm optimizing a batch of them. So I'm optimizing B number of queries at the same time. And the big thing I want to make sure is actually satisfied is I want to make sure that the elements inside of this batch are also far from each other. They're also different enough from each other. So we run a few heuristics, honestly, to make sure that these elements in my batch are far enough from each other. And the problem of coming up with a good batch is this problem of maximizing the average pairwise distance between the elements inside of the batch. So this is called the max sum diversification problem. It's shown to be NP-hard. So obviously, we don't have like that much of hope of finding the optimal thing here, but we use these set of heuristics to just find the best batch possible. So I don't want to go through all these heuristics. So the idea is, can we approximate it, and we are approximating this with various heuristics. So the simplest thing is I'm going to greedily pick the best one at every time step and pick the best elements here. But the problem with greedy is now, like, if my batch size is 5 and I'm selecting 5 points from here, the pairwise distance between them is still quite small. So 1 and 2 are not that different from each other. So 1 and 2 are not giving me that information. That much information. So we've ran a few other heuristics. I'm not going to go through all of them. Maybe I'll just briefly talk about the last one. So this last method we are using is called successive elimination. And the way successive elimination works is we are going to choose the closest 2 pairs. And then after that, we're going to remove the one with the lowest entropy. And we just keep repeating this. So I'm going to choose these 2, remove the one with the lowest entropy. Choose these 2, remove the one with the lowest entropy. And I would keep doing that until I'm left with the right amount of samples that I need. In this case, it's 5. And these are kind of the 5 samples that are far enough from each other and are informative enough for my batch to use every time I run the algorithm. Okay. All right, so here are some results here. So the green is going to be the normal active learning method without any batch, like using any batch. Obviously, that's going to converge much faster than everything else. And this successive elimination method also converges fairly okay, considering like kind of a batch size here. And obviously, it's going to be worse than the non-batch method, but it performs relatively better than some of these other heuristics. We also looked at this for this particular driving example. So for the driving example, we kind of see the same type of plot here for convergence. So non-batch converges fairly fast. Successive elimination at some point reaches the batch method. The other interesting thing is the time, though. So as you can see, the time of the non-batch method is much, much worse than the successive elimination. So timing-wise, we would be doing a lot better when we have a good batch size. And then in addition to that, one question might be, well, what is a good batch size? So what would be a good size to pick? So here this plot is kind of showing that. So we're looking at different results of convergence for different batch sizes, and we have the timing of each one of these batch sizes here. So the idea would be if you have limited time, then you can pick your specific time, and that gives you a batch size. And you kind of see the convergence results there. We don't have theoretical results connecting these two here. So this is all done like experimentally here. Okay. All right, so I'm going to just quickly show this for 2 examples. So this is for the driving case. So with no prior preference, I have no idea what I'm doing, so I'm doing crazy things. And then after 30 queries, our car is learning heading preferences. So it learns like what sort of heading it should keep. And then after 70 queries, it finally learns to keep heading and then do collision avoidance. And finally just learns humans' preferences. So this is learning humans' preferences without any driving data. It's just from like 70 comparisons between generated trajectories using the batch active learning method. We've also like ran this for a bunch of different experiments. I'm not showing all of them. The only thing I have here is the tosser example. So this is the Mojoko example where we have an agent that is tossing a ball inside either one of these baskets. The green basket is preferred. So at the beginning, it doesn't know what the preference is. And over time, it kind of learns how to throw a ball and how to throw it in a basket, which is kind of cool because it just like on its own from comparisons is learning throwing and learning how to throw it in a basket. So like it's a lot of things to learn, basically. Okay. All right. Okay, so just to summarize kind of this part of the talk, well, the idea here was demonstrations. Getting demonstrations is difficult. Demonstrations can be noisy, cannot be really what we were looking for. So maybe we should be looking for something else like comparisons, pairwise comparisons, and try to use pairwise comparisons to learn humans' preferences. And specifically, we looked at this active method where we actively synthesize new queries to quickly converge to the true human reward function and minimize the number of queries required to learn humans' preferences. And then after that, we realized, well, each one of the queries take a lot of time to be generated, so instead can we use a batch method. And by using a batch method, well, we reduce the query generation time. And in addition to that, we can even parallelize things because if I want to learn the human preferences of a population, I can just run them at the same time, and I don't need to wait, like sequentially wait for the responses to arrive. Okay. So some of the directions that we are thinking about going from here, like about this project is, if you think about it, I've been looking at this single reward function that's a linear combination of a set of features, right? And that reward function alone might not be very representative of what humans are doing. So we are trying to look at more interesting models of humans, like mixture models, and trying to learn humans' preferences when we have these more complicated models of humans. And there are some interesting theoretical questions there because pairwise comparisons are actually not enough for us to just learn like these mixture models. If I have a mixture of Gaussians, let's say, representing what my humans do, which is a good model of humans because maybe humans in Boston drive very differently from humans in Palo Alto. So then you actually might have a mixture model. So if you have that type of model, pairwise comparisons are just not enough. We actually need to like go to a higher level and ask for a full ranking of trajectories to try to learn these. So those are some of the theoretical directions we are looking at. We're also thinking about combining comparisons and demonstrations and kind of get the good side of the both worlds to quickly learn better models of humans. I don't know what I have after this. Oh, so I was just going to wrap up. So this is kind of the beginning picture that I had. Oh, these are some of the things we were doing in my lab today. So we are interested in human-robot interaction and collaboration. So in general, we are very interested in collaboration, shared control, trying to predict humans' intent from, let's say, just visual data. We are looking at learning teleoperation maps. So how can I like teleoperate a robot with high degrees of freedom to do tasks? We're interested in social navigation. So if I have a robot that navigates in crowds of people, what sort of actions should it take? How should it interact with people? And also, we're doing some work around safety where we are thinking about safe learning. So if I'm actively gathering information, if I'm exploring, can I do that in a manner that's considered safe? Like how would I do safe exploration about the environment or the state of the other agent? So these are some of the directions that we are currently looking at in my lab. There are some other directions that are interesting. I don't want to go through these slides. Sure, I'll go through these slides real quick. Another problem that we might have is, if you remember my nested optimization, this was kind of the optimization I had there, right? I was assuming that my humans are optimizing this RH, this reward function, and this is assuming humans are optimizers of a rational reward function. And if you think about it, humans tend to be not very rational or optimizers when it comes to a lot of scenarios. So that's the outcome of the curve. What's that? He might have a complicated reward function. That's true. So that's actually what we are looking at right now. So we are interested in thinking about how humans drive when it comes to near accident scenarios. Not this scenario, but near accident scenarios. And there's a lot of interesting work from behavioral economics that thinks about similar type of problems, like this idea of prospect theory, which is thinking about how humans behave when it comes to high gain and high loss situations. And they might not be optimizing a particular reward function. And kind of some of these ideas is the fact that humans are not irrational, but they're bounded rational. So they have bounded resources. Maybe they have bounded time or bounded memory to quickly decide in these challenging scenarios. And the idea is, can we use some of these knowledge that exists in behavioral economics to model humans in scenarios that are challenging or near accident settings? Yeah, maybe let me just talk about this real quick too. So that's all good, right? If I can model humans, maybe I have models of my human-driven cars. And at the end of the day, I need to plan for my autonomous car. I need to figure out what the autonomous car should do. And sometimes when I model humans, this too safe a strategy for the autonomous car just doesn't exist. If I want to be safe and if I want to assume my humans fall into some space, then sometimes I just cannot find, my controller will come out infeasible or unrealizable, and it would say, well, that just doesn't exist. The thing you're looking for is not going to be safe. And this is not a crazy idea. Even Google, that's trying to go fully autonomous, they have around 300 disengagements in 400K miles of driving. So that's about 1 disengagement per month for a typical driver. Disengagement means that the car doesn't know what it's doing. It's transferring control to the human, or the human feels unsafe, so the human is going to take over control. So if we want to have that many disengagements, we need to have better ways of handling these challenging scenarios. And one way is this idea of transfer of control, but I know people have mixed feelings about transfer of control to the human, especially considering humans' reaction time. If it is 8 seconds, lots of things can happen in 8 seconds. But we should have better ways of thinking about these challenging, risky scenarios, maybe have a supervisor that takes over control. And I'm sure that's something that Google is thinking about these days too. But in general, we are interested in being able to diagnose and repair and understand what caused the failure. And again, this is not just about cars. This is about human-robot interaction too. If a robot fails at doing a task, it shouldn't just come out and say, well, sorry, that didn't happen, I failed. It should just come out with some reasoning of why it failed, what failed, what was it that you weren't able to do, and have this kind of iterative process between the human and robot to just do tasks better. And finally, kind of another direction that I'm very excited about these days is taking this whole idea of human-robot interaction in autonomous driving to a higher level when we are thinking about networks of vehicles, when we have multiple autonomous cars and multiple human-driven cars. And thinking about how interactions between autonomous and human-driven cars can affect kind of social objectives like traffic. So for example, if I have a set of trucks that can platoon and get behind each other, maybe that can actually help with the traffic that we would see on the roads. And how can we do that in an efficient manner? All right, that's all. This is the lab. I can take any questions now.
So generally, it seems that creating cases is really important with these mathematical models. So, how is the human driver going around? What are the environmental conditions? So how many of these cases are inherently built in the models versus the model almost creating new categories that it then acts upon?
Yeah, that's kind of like test case generation, right? If I want to make sure that my models of the car driving is going to work out well, I need to generate new test cases. So another project we're looking at right now is actually automatic test case generation. How can we automatically generate new interesting test cases? The type of approaches we were thinking are similar to the active learning type of approaches I was talking about. So there we were actively generating scenarios to figure out model of human. Now we want to actively generate new scenarios and informative scenarios that can tell us something about driving of the autonomous vehicle. So that works very well if everything falls into the model that I have in my simulator. The other problem is most of unsafe settings could happen because it's not even in the simulator. So it's not, it's like unknown. I didn't know that I should model that in my simulator. And those are harder to catch even, yeah.
How much data do you have access to of actual driving scenarios on the highway? And can you use that to make models of, okay, we appear to have a big batch of Boston drivers or New York drivers versus more civilized California, Northern California drivers.
So
come from
most
Boston.
of the work I've talked about here, we collect our data on a simulator. So we have the simple simulator where we can do fancier controlling, and then we have this force feedback simulator where we actually feel the forces, and it's like a little bit more realistic. And here at Stanford, we have the CARS Center, the Center for Automotive Research. So there, they basically have like a Honda sitting in a room, kind of like this, and there's like a screen around you. And you can basically sit in the Honda and drive. And that's kind of where we look at collecting data. We had some data from car companies too, but most of it was just like 101 driving data. And yeah, so the how much matter with, if it is all like 101 driving data, it kind of like all looks the same. So the informativeness of the data or kind of like diversity of the data is the main thing that would be interesting for us to look at. Yeah, I haven't seen much public data on like Boston driving or like Palo Alto driving. But yeah, every company, for example, is collecting just their own data sets. Yeah.
One advantage of the multiple car scenario, though, is that other cars are doing experiments for you. And in fact, you can drive around with a camera and observe a lot about how people actually respond to the experiments inadvertently performed for you by other people. Does that help?
Yeah, so there is some data sets of like just cameras. So there's this NGSIM data set, which is a public data set that's online, that is just a camera looking at a highway and looks at like basically cars arriving. So it depends. So for the traffic work we are looking at, like traffic data, like that high level data of just cars like passing by is probably good enough. For like lower level, I want to actually control this vehicle. I want to know the location of my car. I kind of want to have a good sensing of where the other drivers are. So for that, it's harder to find like data sets.
But the other cars are in proximity and they're doing the experiments you want to do.
Yeah, so for example, yeah, you're saying I could put like a sensor on my own car and then drive around and get some data?
Yeah, but watch all the other cars. Yeah. Essentially censor every car on the road because they're all doing experiments on each other.
Yeah, but like we don't have sensors on all the cars on the road.
You don't have to, it's optics. When I said I watch a car and I notice it doing goofy stuff, people drive that way.
Yeah, so it's a combination of like that NG, like I'll have images of cars driving versus like some of these works, like it could technically work from images if you really like try to, but like what we're looking at is just looking at acceleration.
You've got to follow them for a while to notice because each car is going to be a different behavioral function. And then there's how they respond to each other, and some people interact badly with each other and some people don't.
So we could collect something like that.
Generate a bunch of different models.
Yeah, and that's actually very interesting because like when I think about this, the interaction work I talked about, you might say, like, I'm going to slow down here because I just saw that car like taking over that other car. So you look at the interaction of other cars with each other, and that affects your actions too, which is not something we haven't modeled that here, but that totally affects your actions too, and that's kind of another layer of thinking about interaction.
And it certainly gives you a model of both cars.
The planning horizon you're using is only half a second. It puzzles me how you can get much information about what the other driver is doing with a planning horizon less than the human reaction time.
So the model of the human, so the active information. So because for the first work, we're not doing active information gathering, right? If you're not doing active information gathering, the model of the human is learned offline. So I'm not like, we are not trying to update it in an online fashion in the first work, right? So I'm just looking at how humans drive offline. Then in an online fashion, I just see what their state is, and I just evaluate my function of my reward function in that state. So I don't need to like observe a history of the human or like 0.5 seconds of human driving to update that, because I already have a model of how normal drivers drive. For the other kind of active information gathering type of work, we are doing the nudging in type action. So with that, we can kind of observe what people are doing and have this belief kind of going over time. It's not just, the belief is going to be a longer term thing. It's not just for the planning horizon. So my belief of the driving style of the person, if it is 50-50, aggressive, not aggressive, I'm going to keep that belief until I see that, like for the full period of time that I see that car. Does that answer the question?
It seems like that 7 or 8 second human reaction time is from reading a book in a fully autonomous car to getting full situational
Yeah, so
awareness.
the 8 second is for that. Yeah, the 2 second is like normal or something. Was it 2 seconds?
I
don't remember.
I don't. Than that, more like 3/4 at best.
I don't think
or,
so.
Or maybe
I think
maybe
kind
a
of
quarter
large,
for actually reacting to something.
I actually think it's quite large. I think it's around like, I think it's quite, I don't remember the like literature like that. There's a study in Germany that looks at kind of like all versions of it, but I don't remember the exact number. But I remember it was high. It was like something.
I mean, if you're paying attention, if you have a 1 foot ruler and you have somebody let it slip from their fingers with you holding on the other end, most people can catch it before it goes through, and that's a 1/4 second.
Yeah, but for driving, like specifically for driving,
right.
I'm like very sure that it's like longer, way longer than the planning horizon that even like normal autonomous cars use. Like not even like modeling humans. Like usually autonomous cars use a 0.2 second like for planning. So it's definitely like longer than that.
Yeah, I mean the state of the amygdala is going to affect which mode the human is in.
Yeah.
So how's Google doing it, or Tesla? What kind of method? You know, I don't know. That's probably
yeah, so I don't know because like they don't tell us like the exact details of it. But from like what we see, like they have started thinking about like different models of humans and kind of taking that into account as opposed to previously, like I remember, like, I don't know, 2 years ago, like even when you talk to car companies, the way they would model humans is they would model them as agents who are just going constant velocity. So if they're going 60 miles per hour, they're just going to keep going 60 miles per hour. It's not that bad, honestly, because if you're doing MPC, like even if you assume this person is going 60 miles per hour, I don't know, next second, like it's not hurting you too much. It just makes you to take like more conservative actions because you think that person is not going to be ever affected.
One of the things that I realized through managing different cars is that they, rent a lot of cars. So, and some of them come with sensors that actually, kind of direct how you drive, pretty much, right? Like you're going too fast and then you're getting close to a car, you get this big, sound that you kind of like makes you, makes you stop or slow down. Yeah, it's kind of like where all the auto companies are heading to now, like trying to drive the human.
Yeah, to operate the human, yeah.
Right, which is interesting.
Yeah, so that goes to shared control. So there are like different ways of like doing shared control between humans and robots. Yeah, it comes into human-robot interaction too, so that's it.
Yeah, that's why it's so interesting. Yeah. Thank you. It's great.
Cool. By the way, the military teleoperates UAVs with more people than normal.
So there's a precondition for all of your work to be useful, and that is that the environment that you're running in, the hardware and the software and the compiler and just all of that crap has to work.
Has to work. Yes, yeah, I agree. Here I'm assuming everything works. If they don't work, then we can just make our algorithms a little bit more conservative. So if I can model that well, with some uncertainty, the system is going to fail. Maybe I shouldn't trust my actions as much. So you can kind of just propagate that uncertainty back into planning and make your actions a little bit more conservative. So if I think my model of the human is not exactly right, or if I think I can't sense the human like exactly right with this probability, then I'm not going to cut in front of the person. I'm going to like slow down and all that.